Well, hi everyone. As Robert said, my name is Jackeline S Rechy-Garcia. And first of all, I would like to thank to Marcelo and the organizer for inviting me to share my last paper. So thank you so much. And I'm going to talk about my last paper, which is titled Dissecting the Compact Planetary Nebulae M2-31 with GTC MEGARA. And this work is in collaboration with my friends. You can find their photos and their name in this part. And I'm a postdoc in IRIA, UNAM, working with Jesus Toela. Well, as we know, planetary nebulae represent a highly evolved stage of low intermediate mass star, more or less 1 to 8 solar masses. And the densities are 10 to 4 particles per cubic centimeter for slightly extended young objects, and 100 particles per cubic centimeter for extended young objects. The electronic temperature for planetary nebulae is 5,000 to 20,000 Kelvin, and the surface temperature for the central star is 20,000 to 300,000 Kelvin. So in this image, you can observe a different morphology of planetary nebulae. So we can observe a bipolar structure, quadrupolar structure, ellipsoidal structure, nodes, etc. No? So in the past, it was believed that the most planetary nebulae were round, but now it is known that approximately the 80% of planetary nebulae are asymmetric, showing a ellipsoidal, bipolar, or multipolar morphology, displaying tori, jets, nodes, etc. A recurring question is how can the formation of such a component be explained? Well, in order to answer this question, different options have been proposed. One of them is magnetic fields. So this is a model by Garcia Segura, and they consider magnetic field, and you can observe bipolar structures in this model. And also there are other paper by Sabin et al. In 2020 that they found the presence a well-organized magnetically collimated structure in a nebula. Also, it's currently accepted that a binary system gives birth to such bipolar structures. So here you can observe a model by Sol in 2020, and they found a bipolar structure considering binary interactions in the central part. So you can get more details in each one of the paper. Well, now we know that planetary nebulae present a big morphological variety, and this indicates complex material ejections, including between the stellar winds with the different degrees of symmetry and the action of high velocity collimated outflows. In this image, you can observe a different morphology of these beautiful objects. And for example, we have ellipsoidal structure or point symmetric structure, etc. No? The morphological variety is very, very big. Well, the morphological classification is often done based on an image. Therefore, the classification can be compromised by the image quality. Also, high dispersion spectra in the H alpha and nitrogen 2 are used to find evidence of fast collimated outflows. In my PhD, I studied planetary nebulae with round appearance, you can observe here. But the spectroscopic observation reveals outflow moving at high velocity. These objects are very compact, no more than 12 arcseconds, and I propose call them spectroscopic bipolar nebula. For the case of M2-32, N1-32, that is imaged by Guerrero, we have an observation obtained in Observatorio Astronómico Nacional in San Pedro Mártir, Mexico, And this is N1-32. This is the same image, but in a great scale. And we have different red rectangles here that correspond to the different slits that I use for this work. And check the middle, the central region. For the position velocity maps, you can observe two bright knots in this part, and also material moving at high velocity. So in order to confirm if this planetary nebula has a jet, we make a hydrodynamical model that consists in a jet and a toroidal structure. And this is the position velocity map, the synthetic PV map that we obtain with these hydrodynamical models. And you observe two bright knots in this part that correspond to this in the observation. And also this material moving at high velocity too, as the observation. So from here, of this hydrodynamical model, we confirm that this planetary nebula has a jet, but this jet is moving in the line of sight of the observer. That is why the jet is not seen in the image, because this jet is moving in the line of sight. So, well, this is there are the three planetary nebulae that I studied in my PhD too. And the red rectangles and black rectangles are the different slits that I use with different position angles. And in order to study the morphokinematic analysis, it's necessary to locate a slit at different position angles in a nebula. When these objects are small, is not necessary to put a lot of slit, but when the object is very big, it's necessary to by placing a slit map in order to map all the planetary nebulae. So now we have another technique that the name is integral field unit, or IFU. And this is an observational technique that provides spectral information over to the field of view. And applying this technique, we obtain a spectrum of all points of the fields and a simultaneous way. In the case of long slit spectroscopic, well, this only provides some spatial information only when where the slide was located. So in our case, the integral field spectroscopy that we used was MEGARA, that in Spanish means multispectrógrafo en GTC de alta resolución para astronomía. And this instrument, well, this is a model done by INAOE with they present the different components that MEGARA have. And this instrument is attached to the Gran Telescopio Canarias, that is located in Canary Island. And this instrument has two modes of observations. The first one is the large compact bundle IFO that you can observe here. And the second one is the multi-object spectrograph. And in our case, we use this mode in order to study the spectroscopic bipolar nebula, because check the size is 12.5 arc seconds times 11.3 arc seconds. So this mode seems designed especially for the study of spectroscopic bipolar nebulae. And also using MEGARA, we have the opportunity to get an image and a spectroscopic observation in a simultaneous way. In this plot, we have the different volume phase holographic. In the horizontal axis is the wavelength, and in the vertical axis is the resolution. In our case, we use the BPH with the highest resolution, covering 6004 angstrom to 6700. angstrom. This cover lines to nitrogen, to H alpha, sulfur, etc. Well, the scientific interest of MEGARA, well, can be used to study galactic and extragalactic nebula. In our case, we use MEGARA in order to study planetary nebulae because it helps us to study the spatio-kinematic structure with unprecedented details for the various structural components. And this is the MEGARA science teams. Of course, they are from for different countries and for different institutes too. Well, we studied other planetary nebulae using MEGARA. The first case is HUBI-1, and the red rectangle is the MEGARA observations, and we found material moving at high velocity. And with MEGARA, we found that this material corresponds to a shell-like structure moving at 250 kilometers per second. The second study of using MEGARA was NGC 2392. This is a known planetary nebulae, and each black square here correspond to the different field of view of MEGARA, and we obtain an image of the jet of this planetary nebulae for the first time. So the jet is in red and blue, so it provides detailed information of its morphology and its kinematic. And well, now we have other observations using MEGARA. This is other planetary nebulae. And we found that the jets of this planetary nebulae are moving at velocity, at high velocity, more or less 220 kilometers per second. So if we confirm that, it will be one of the planetary nebulae with the highest velocity. But well, maybe in other meeting, I'm going to share the results. Well, return to M2-31, that the planetary nebulae that we studied in this case. We studied this planetary nebulae using traditional techniques, the optical image and long slit spectroscopy using ALFOSC at the NOT in La Palma, Spain. And also we have a program to study spectroscopic bipolar nebulae using integral field spectroscopy as MEGARA, that I explained it some slides ago. So who is M2-31? Well, this is a compact planetary nebulae. It has an angular size of 4 arc seconds times 3.7 arc seconds. This is very compact, as you can observe. And this is located at a distance of 5.9 kiloparsecs. This planetary nebulae belongs to the group of spectroscopic bipolar nebulae. And it has a collimated bipolar outflow in expansion velocity reaching 90 kilometers per second. And in previous work, have found that M2-31 has a warfajet carbon-rich WC46 central star. And in the optical image, check this. In this part is a knot at the north direction, and in this part we have other knot and the south direction. In this part, you can observe this emission that corresponds to the knot at southwest directions. Well, with the MEGARA observation, we are able to get a pseudo slit using Q-FITS view software. This is in yellow and orange rectangles are the pseudo slit using MEGARA. And subsequently, we build position velocity maps or PV maps at different degrees. So the slit at 10 degrees along to the north and south knots, to the 50 and 60 degrees along to the north at southwest, and in 140 degrees along to the intermediate position. So this is the PV maps in this image. at different degrees that correspond to the slit. So we found that this planetary nebulae has a radial velocity in the local standard rest at 170 kilometers per second. And check all these PV maps. In all PV maps, you can observe two bright blobs. The first one, that I put the cursor here, is moving at 150 kilometers per second, and the second one is moving at 190 kilometers per second. For the case of the PV map at 60 degrees, you can observe this emission here that correspond to this node at the southwest direction. And also for the case of the PV map at 10 degrees, this emission that you can observe here and here correspond to the nodes at north and south. For the case of the other emission lines, but especially for the carbon-2, you can observe that this emission line is more concentrated in the central zone compared with the nitrogen or the other emission lines. Well, the above was analyzing the observation in a traditional way, but now we present a more detailed analysis of the kinematic structure of M2-31. And using this technique, we found 5 kinematics components with different spatial extent. So the first row correspond to the normalized flux with the different contours. And the second row correspond to the velocity tomography. So the leftmost and the rightmost column show components protruding from the inner core with the fastest velocities. So we call to the spectroscopic outflow. For the red component, is moving at 200 more or less kilometers per second, and for the blue spectroscopic outflow, moving at 100 kilometers per second. Also, 2 inner shell are found in this planetary nebulae, and yellow and turquoise color, and they are moving at 180 kilometers per second and 140 kilometers per second. And finally, the 5th component is in the central part that disclose a pair of slowly expanding structures. For the case of carbon-2, we found that this per-meter line is more concentrated in the central zone with a smaller diameter and with an expansion velocity that is less than nitrogen-2. So, in order to understand these 5 components in this planetary nebulae, we extract the contours from the flux maps, and we overlay them on the M2-31 in a gauge scale image. This is in order to assess the connection between the kinematic feature and the morphological structures. So check the spectroscopic outflows, that is red and blue, that are in this part of the nebula. And the black line correspond to the low velocity component. For the second image, you can observe the inner shell in this part. And finally, the carbon-2 is located in the central region. Well, to study for this planetary nebulae, we studied the spectral type of the central star in the orange region, and you can observe here the spectra. And this spectra show other line and exhibits the presence of the classic broad warp jet. So these broad lines are known as violet, blue, and red bone. So here you can observe a zoom of these emission lines. These spectra show other emission lines that are characteristic of warp jet in oxygen sequence. And we did a carefully inspection about the flux, the different ratio, the equivalent width, and considering all of this, we found that this central star correspond to a warp jet in the oxygen sequence form. And finally, we calculate the chemical abundance for this planetary nebulae. And we obtain this temperature and this density that correspond to a young planetary nebulae. And considering the helium abundance, this planetary nebulae belongs to a type 2, but according to the nitrogen abundance and nitrogen to oxygen ratio, this planetary nebulae is rated at type 1. Well, finally, the summary, we found that this planetary nebulae, M2-31, has 5 principal kinematic components, a pair of fast spectroscopic outflows, and a receding and approaching components, a low velocity component, almost orthogonal to the spectroscopic outflows, and to NOT as north and south. And this is the first time that the flux velocity and width 2D maps of the carbon-2 emission line are presented for a planetary nebulae. And this line is more concentrated in the central region than nitrogen-2. The central star for this planetary nebulae is reassigned a spectral type of Morphological in the sequence of the oxygen sequence form. And well, thank you so much. If you have a question, you can ask me.
Thank you, Jacqueline. Do we have questions? There is a question in the chat from Solon, who's asking, is the chemical stratification in the outflow the planetary nebula a typical observation as in this case? How does the stratification occur?
Yeah.
If I understand the question
correctly. That is right. That you got it. That's right. That's right.
Well, I don't understand very well the question, but for the case of for the case of carbon-2, this is
the carbon and the nitrogen. You're getting a smaller shell with a carbon and a larger one in the nitrogen case. I think of those
yes.
larger outflows, right? So there seems to be some form of a stratification.
Yes.
In chemical abundances, somehow. So is that a common thing? Do you usually get such a thing? I don't know. That's what I was wondering. That's all.
Yeah, the idea is that there are other jobs that they have a maps in permitted line and in excitational collisional lines. For example, in Garcia Rojas and in Rechy in 2017. And they found that the permitted line is usually is more concentrated in the central zone. So they conclude that a planetary nebulae could have multiple plasmas stratification, considering different plasma that come to other plasmas. So the idea is that a planetary nebulae present different multiple plasmas.
Okay, thank you. Thanks.
And we also have a question that regards the classification, I think, of planetary nebulae. So Gagit Topmasian is asking how justified is to call a PN with a central Wolf-Rayet star.
Well, in this case, we studied the central star using NOT ALFOSC. So we justificate to call because this the spectra of this central star of this planetary nebulae present broad emission lines that are similar to the spectra that show in the massive Wolf-Rayet star. So considering this, only for the spectra are very similar, we call to a Wolf-Rayet type. The difference is that in the central star of planetary nebulae, the mass is more or less than 1 solar masses. So in the other star, the stars are very massive.
And I can see a comment from Domitila De Martino saying forbidden lines form in low density environment, possibly explaining the different forming regions.
Yeah,
And,
yeah.
I think this was referred to Solen's comment earlier.
Yeah, could be, but I'm not sure. I think that we need to study more this multiple plasma in the planetary nebula.